Hi, everyone. Welcome to another episode of The Blind Spot, the podcast for the curious about science and the new ways of thinking about science, not just the old ways, because the old ways are the old ways and we need new ways. And that's what this story is about.
Well said.
And, right? We've been doing that stuff for 400 years. It's been awesome, but it's time to kind of rethink some of the foundational issues related to that old science, and that's pretty much the main goal so far in our conversations. And so to make the point, today we're going to talk about thermodynamics, or the science of heat, that you may think it's not as sexy as mechanics or electromagnetism or quantum mechanics, but the truth is it is the sexiest. It is the
sexiest.
Right? You agree? Actually, Einstein has a famous quote about thermodynamics. So there are three fundamental laws of thermodynamics, right? And he said that all laws of physics could change in the future, but for the three laws of thermodynamics. Now, that's quite a statement, right? Because it's saying something about why thermodynamics is different from the other kinds of physics that we talk about. And I think one of the reasons for that, and correct me if I'm wrong, Adam, is because thermodynamics really is closest of all this physics, kinds of physics that we discuss. It's the closest to our perception of the world in a very kind of like experiential, visceral way. It really is the science of heat, and cold and transfers of heat and how it works. And amazingly, and maybe we'll do a little brief history today of thermodynamics and where the foundations are.
Because we can always come back later to other elements, but really introducing this to people, I think, is worthwhile.
Right, because amazingly, the idea of what is thermal equilibrium and thermal non-equilibrium in its relationship to the nature and the flow of time, these things are all deeply enmeshed. Right. And I think that's just fascinating.
And I think, the thing that people don't understand, they hear thermodynamics, which is actually what, this was my reaction as a freshman. I was like, heat engines.
I know, refrigerators.
Right? Yeah, right. And when I first took thermodynamics as an undergraduate at the University of Colorado Boulder, I think it's the only class like I got a C in. Because I was just like, oh God, if I have to see one more Carnot diagram of a refrigerator, I was like, I don't care. Like, I'm sure some of these are cool to build, but I'm not interested. So I had to take it over again. And the next time I took it, the guy also emphasized statistical mechanics. And my mind was blown. Like the mix of like boots on the ground experience combined with the highest levels of abstraction of, hyper dimensional phase spaces where the solutions to these problems live just blew me away. And what I want, people should understand that it's not only are we going to deal explicitly with time. Why does time flow in only one direction? That's going to come out of thermo and stat mech, but also life. If you want to understand life and everything that life does, including human civilizations, it's going to be thermodynamics. You're not going to use general relativity or quantum mechanics to understand why there's consciousness, why creatures are sentient. You're going to use thermodynamics and stat mech. And it's going to turn out even that there's a deep relationship between information and its use and thermodynamics and stat mech. So it is by far the most profound subject in physics, even though it sounds like the least profound subject in physics.
I know, funny, right? Because we have to situate things, right? By the 19th century, so 1800s, there was mechanics, the whole Newtonian stuff, the universe is a clockwork, right? It's all like a machine-like, and you give me the equations of motion of something, I can predict the future of what's going on. There is the famous story of Laplace. I think we mentioned that, right? That he wrote this book called Celestial Mechanics, where he calculates the motions of all the planets, including perturbations of orbits, and he gives a copy to Napoleon, right? And Napoleon comes back and says, "This is fantastic, Monsieur Laplace, but I do not see the word God in your text." And Laplace famously answered, sir, I have no need for that hypothesis, meaning, the universe is a machine, period, right? And in fact, to illustrate that, and that has something to do with thermodynamics as well, as we'll discuss, he also has this thing called Laplace's demon, where he says that if a intelligence could know the positions and the momenta or the velocities of all the particles in the universe, this intelligence could apply the laws of mechanics to predict the future perfectly, right? So this is sort of like the most, how can I wouldn't say obnoxious, but the most pretentious argument you could make for everything is a machine, and so it wasn't really a matter of principle, it was a matter of practice. How can you possibly get all these positions of all these particles and measure not just the position, but the velocity also at the same time, which is a problem for quantum mechanics, but he didn't know that. So this Laplace's demon was basically saying that everything could be described mechanically, right? And so that was the one pillar. And then the other one, also from the early 1800s, is electromagnetism, right? The theory of electricity and magnetism, which is a different kind of physics, incredibly fundamental, which was discovered sort of in separate, really, because people started to get shocks and they knew materials were magnetized, etc. So they developed this theory where the biggest output of the theory, apart from any others, is that light is an electromagnetic field propagating in empty space.
And that's like the 1850, right? I think Maxwell's equations are somewhere in like the early part of the second half of the 19th century. Yeah.
It's like 1860 something.
Yeah.
Yeah. I know it because at King's College, where I did my PhD, he was there when he wrote these equations. Cambridge had Newton, but we have Maxwell kind of thing. And by the way, right? It was like, but then he went to Cambridge, I think, if I'm not mistaken. He went somewhere, either one of the two, I think first Cambridge. I know. But he's also fundamental for thermodynamics, actually, because he's
later on, right?
Right. The third thing that was going on in the early 19th century is people were developing steam engines, and they wanted to improve the efficiency of steam engines. It was an engineering problem. It wasn't really a physics problem. So all the big guys, in the beginning, were engineers that were trying to improve the efficiency of those machines. But then they realized that there was a limit to the efficiency, that they just couldn't make it better, And Carnot came and said something about the law of something that became the law of entropy, the second law of thermodynamics, right? So the first law says that energy is conserved, basically. You can change the kinds of energy you have. You can go from, for example, a car, right? A car, you turn on if it's an old-fashioned gasoline car. Now that I have electric, I can say that. So much better. Anyways, in many ways, nope, not perfect, but in many ways, it's that you ignite the gasoline with a spark, and the chemical energy stored in the molecules of the gasoline propel the pistons. They're going to transform then this chemical energy into mechanical energy, and this machine is going to move forward with wheels, etc. So energy can be transformed, but it cannot be made from scratch, so to speak, right? I mean, it's just there. And the second law is a second law of thermodynamics, right? Which is the beautiful, weird, somewhat mysterious thing.
Still mysterious. I think still mysterious, even after all these years, yeah.
Which basically says that there is a natural tendency in any system, as long as it's not connected to the outside world, so it has to be an isolated system, where this stuff inside this isolated world, be it, say, a gas in a box, which is the typical thing that we always talk about. In fact, we did talk about this in the past, will tend to go to its most disorganized state possible. So, for example, if you manage to put a bunch of molecules of a gas in a box and squeeze them at the bottom corner, and you let go, they're not going to stay there. They're going to spread out evenly across the box, right? And this tends to be described as an increase in entropy. And the final equilibrium system is the one which is the most featureless possible system, arrangement of this molecule, which is basically that you would, if you look to the box with a little microscope, on average, you have the same probability of finding a gas molecule in a certain volume.
A couple of points here. Just so first of all, all right, so there were these three pillars of science in the beginning of the 1800s. One of them, which is thermodynamics, is actually it's an engineering problem. And I think that's really important. People were building steam engines who really weren't thinking about physics. There was no theory of heat, right, at all. People have just found like, oh, if I heat something up, I can boil water and I can make the water push a turbine. And, so it was like, I think it's very important to think of when we think about the origins of thermodynamics to see how closely connected it was to daily life. It came out of people trying to build stuff and make it better. And then those two laws, just to step back a little bit, when people start to think about it, start to theorize about it, you end up with these two laws, the first of which is the conservation of energy. Great. There's only a certain amount of energy, but you can transform it into different kinds. It can swap from one form. It can swap from magnetic energy over then into the kinetic energy of motion. And then also, this was new too, heat. This thing called heat was a form of energy. And heat was really, and what we're really interested in is the flow of heat. Really, heat was actually, about the flow of energy from one place to another.
Right.
And then comes the second law, which has got this super profound weirdness in it, which is that when systems transform, when energy is transformed, there is no way to avoid the generation of entropy or of disorder, which means that unless you have like a very, very rigorously controlled system, as you said, fully isolated, anytime you use energy, you generate waste. Anytime you use energy, some of that energy is going to turn into an unusable form, a wasteful form. So like if you have a gallon of gasoline and you want to move your car from here to say Buffalo, New York, I'm in Rochester, New York, sure, fine. Some of that energy in the gasoline is going to go into just heating up the engine block, which I can't do anything with. That's not going to help me move the car. Some of the energy in the gas, the gasoline, will turn into just waste heat, into just heat.
Right.
And that second law is so fundamental. And so the implications are so profound. We're going to find in it everything from the reason why time only goes in one direction to also why you die, which are connected. The reason why you're going to die is because of the second law of thermodynamics. So the second law, which people were really using because they just wanted to make better heat engines, actually is going to flow into science in a way that is going to have the most profound implications for understanding real things, complex things, not abstractions, quantum fields. I mean, quantum fields are great. Even quantum fields, you'll have to deal with entropy, but like really kind of boots on the ground, complex, macroscopic systems.
And there is the notion of work, right, which was invented precisely for that measure. Okay, how much work can I do when I do this transformation of energy, which is basically a force that is going to move something for a certain distance, right? And a very efficient engine is the one that can do the most work with the least amount of energy, right? So that's efficiency, right? I mean, I do a bunch of work with the least amount of energy. That's the optimization problem that the engineers had to do. They say, I want to do work. I want to lift a heavy block by a certain amount, by using a mechanical device. And that device may be propelled by steam, right? So you heat up the water, it boils, you make the wheels of the pedals of the wheel spin around, and then eventually you're cranking up that metal block, and it's going to go up by a certain amount, which is basically the amount you're doing work against the gravitational force, like you're lifting some. So it's always related to that kind of efficiency problem, right? And what probably pissed them off is that you could never have a perfect engine, that some of this energy is always going to be waste, so you cannot have a perfect energy that does exactly infinite efficiency. And that's as true to an old steam engine as it is to a computer. A computer, you have flowing charges on a computer that generates heat, and it warms up, and because you have to have all these ventilation systems in computers, and that heat cannot be used to make current go along the wires anymore. And it just compromises the efficiency of the computer. And that is why, by the way, cuts to modern times. I just have to say this. I don't know if I mentioned this. I asked ChatGPT the other day. It's completely pertinent to our conversation. I asked ChatGPT the other day the following question. It was, how much water do you need to answer this question? And ChatGPT said, well, this is a simple question. I don't really use it. My servers use water because they need to be cooled down because they heat up, hence the connection. And it's about half a liter, a pint of water per question, right? And then my second question was, okay, and how many questions do you answer on average per minute? And then the machine said 10 million per minute, which means 5 million liters, a little over 5 million pints of water per minute in the world to cool off the waste energy that comes from the fact that even computer servers are not perfectly efficient. That's thermodynamics.
Yeah, that's thermodynamics. Right.
And so you mess up and it goes, it spreads out, right? Because, generating the heat, it's dissipating in the atmosphere. The water cools it, the water gets cooled, warmed up and compromised. And so you need more water. The heat is in the atmosphere. It's causing the greenhouse effect. Right. It's helping out. So it is all connected in that way. So thermodynamics is the science of life. It's the physics of life in a sense. It's connected in all these different ways.
So let's go ahead. Let's mention something and then move forward towards towards statistical mechanics in the end of the 19th century. So one note is, so the second law of thermodynamics says, unless you're like a closed system where you have no connection with the environment, you are always going to generate entropy. So entropy is either as systems evolve or as systems just do stuff, the entropy will either stay at zero or it'll go up. It'll never go down. Right. Mm-hmm. And so people already said there was already the implication like time, time only flows in one direction. So even before people were before we get to StatMech and Boltzmann, who we're about to mention, there was the sense like maybe there's a connection between time and entropy, right? That the universe is just generating more and more entropy as time goes on. And so therefore, that there's a connection between the one-way flow of time and entropy. But then we get to by the end of the 19th century, beginning of the 20th century, they begin to ask the question, like, well, what is really heat? Explicitly, what is heat? At some point, people had thought it was like a fluid that flows from one thing to the other. And it was by the end of the 19th century that the atomic hypothesis people were really beginning to push it. And it's amazing because you now think like, well, of course, everything's made of atoms. But in 1880, it was still very questionable about whether matter could be resolved into those little, bits, those little chunks. And it was people like Boltzmann and people like Maxwell who started to work out sort of the mechanics, like trying to use Newton's laws for like zillions of atoms to try and understand thermodynamics, but from what we call a statistical mechanics point of view, because you're never going to be able to track, every box of atom has 10 to the 26 particles in it, right? You're never going to be able to track all of those. So you have to use statistics and ideas about probability. So Boltzmann and Maxwell and the American physicist, I'm suddenly forgetting his name, from Yale. All right, we'll come back to it. They started to work out what was called statistical mechanics, where you do Newton's laws, but Gibbs, yes. Note, interesting, there is a fantastic scientific biography of Gibbs written by the poet Muriel Rukeyser. Muriel Rukeyser was an incredible poet, but she had an interest in science. And she was the one who said, my favorite quote about science is that the world is not made of atoms, it's made of stories. But anyway, if you can find that biography, it's a great scientific biography, but it's also got the poet's vision of the world. Anyway, so there's this beginning of trying to have a mathematical formulation of atoms and their behavior as the foundation for the first and second laws. And from that, you now get the first real connection between the flow of time and the second law of thermodynamics, in particular with Boltzmann's H-theorem, what's called Boltzmann's H-theorem, where he tried to prove from a particle standpoint, from atoms smashing into each other, their average properties of behavior, how this would always lead to an increase in the entropy, and therefore the increase of entropy was in some sense a way of expressing the forward flow of time. Because here's the problem: in Newtonian mechanics, there's no direction of time. You know, if I showed you a movie of two balls bouncing into each other, I could run the movie forward or backward. You couldn't tell the difference, right? Yeah, you wouldn't know. But somehow our experience is that time only flows in one direction. So how do you take Newton's equations, which don't care about the direction of time, and somehow get a one-way flow of time out of that? And so Boltzmann, using statistical mechanics, made a proof of something that looked like why entropy always increased. And there was your thing about, well, this is why when you have large collections of stuff, this emergent property of the one-way flow of time will appear. And this idea of emergent properties now is going to also flow down into the modern era.
Mm-hmm. Should we give some sort of prosaic examples that everybody knows about related to this flow of time and the growth?
Yes.
And it relates to complexity, which is what we started our conversation with. So here are a few examples, some of them very basic, but very important. Okay, you get an egg. An egg is this beautiful, organized thing that has a nice, in yellow thing inside, and it has the protein outside, and it has this nice skin. You crack it and you fry the egg. Scramble it.
Scramble it. You got to scramble it. Scramble is the important part.
This egg is never going to unscramble back to its original shape and conformation, right? So that's the thing. So this kind of movie, if you make it go backwards, the guys are going to say, this is nuts, man. This is a scrambled egg is going back into a normal egg. That kind of movie is completely different from this kind of movie. Here's pencil going one way. Here's pencil going the other way. You cannot tell watching this movie of the pencil, just this bit, if time is going backwards or forward, because it's indistinguishable. You just can't. But with the egg, you can. Same thing with, let's go more romantic, like a perfume bottle, right? So you get a perfume bottle, it's closed, and then you open it. And what happens is the perfume is made of this volatile material that makes the molecules spread out. Diffuse is the right word that we use in physics. There's a diffusion equation, which is a beautiful thing that tells you how these molecules of perfume are going to collide with the molecules of oxygen and nitrogen, with air in the room, and it's going to percolate across the whole room, so that if my wife comes in here through the back door, she's going to say, ew, who opened the perfume bottle? I hate perfume. So she knows it happened, right? But she really doesn't like perfume, which is okay because I don't wear any cologne or anything like that.
No cologne for you.
It's part of a perfect relationship. Don't compromise on the little things. Don't be a stickler for the little things. Compromise, and it's all good.
A little bit of life advice in the middle of a scientific exposition.
Right? It's important. But then that these molecules of perfume are not going to go back into the bottle spontaneously. So this is another example, and this is the beautiful connection with the H-theorem by Boltzmann. So here we go. You have this big room, right? And this room has a bunch of air molecules zigzagging around at a certain average speed, and you can measure the speed of the room because, as our friend Maxwell mentioned, the temperature, which is another story, the temperature in the room is proportional to the average square of the velocities of the molecule. So temperature T proportional V average square. That's kind of like the formula. Anyway, so you got these guys are going around, and then you open the perfume bottle. Now, what's Boltzmann going to say is that if you make a map, let's make a table of the positions and velocities of each one of these molecules of air in the room, right? Because they are moving around at thermal equilibrium, there's nothing warming up, the average is the same. I mean, on average, you look here, you look there, you look there. They're all going to have on average the same velocity, etc. So the same temperature. When you open the perfume bottle is not going to change the temperature but the molecules of perfume are going to get out and they're going to start colliding with the molecules of air. And you have to now make a table where you have the positions of these molecules of perfume as a function of time and their velocities as they collide. So you make like this really complicated sequence of lists. Time t equals 0, it's this way, and then you open the perfume bottle, they start moving around. Where are the molecules? Time t equals 1, velocity t equals 2, 3, 4. And what you find is that indeed they spread out. So each one of these snapshots, you can call it a phase space portrait of the molecules in this room. So time t equals 1, I can make a list of all my molecules of perfume and their velocities. That's one phase space snapshot. Go again, time t equals 2, do the same, t equals 3, do the same, t equals 4, do the same. There is a probability. So think that the molecules are spreading out into this room, just like like if you're a checkerboard, you know? Like it could be here, it could be here, it could be here. You can label all this stuff up. There is a probability that the molecules are going to be in a specific square at a given time, right? And that is a phase space portrait. There is a probability that given a certain time, I'm going to find the molecules in a certain position in this checkerboard. So you have a checkerboard in this room. The molecules may or not be occupying the slots in this checkerboard. There's a probability that I'm going to be measuring, thinking of the room as a giant three-dimensional checkerboard where the molecules of perfume can be in a specific slot, right? There are many molecules, there are many slots, and they can be in there. And the idea that Boltzmann said is that there is a probability, if you take a snapshot, there is a probability that the molecules are going to be in this slot or in that slot, and that is a phase space picture, right? That's called a state of the system. The state of the system at time equals 1. And then you move on in time, state of the system at time equals 2. The molecules are spreading out. And then this movie is evolving in time, and the molecules are spreading out, and they're diffusing across the room. And more of these slots are going to be filled up as time goes by because the molecules are diffusing. So these are the evolutions of the different states of the system. So the H-theorem from Boltzmann, it tells you what is the probability at a given time that I'm going to find the system in a particular state with so many slots occupied, right? And basically what he says is that as the system evolves into equilibrium, which in this case would mean that the molecules of perfume are equally spread across the volume, the entropy grows, right? And I'm going to have a higher probability of finding the system in that state. So the state of maximal entropy is also the state of maximum probability in the sense that all molecules are going to be spread across the volume.
Yeah, and that's a killer link. What we see now, right, with statistical mechanics, what happened at the end of the 19th century is there becomes a link between equilibrium, right? Equilibrium, which is like the final state. It's kind of death in a way, when something, it's like with your coffee cup. Your coffee cup starts off hot at a different temperature than the environment, and it cools down. When it cools down, it has come into equilibrium with the environment. There's going to be a link between the move towards equilibrium, that systems move towards equilibrium, generating entropy as they do that, and probability. That the most probable state is going to be the state that takes you towards equilibrium. So there's this fundamental link now between probabilities, like we know. So it's really interesting. Physics was supposed to be about absolute knowledge. We know everything about everything. And now you're seeing, even before quantum mechanics, this transition to being like, well, I can't make any individual particle, I can't tell you where it's going to be, but I can say probabilistically what collections of particles are going to look like. So this thing of the H-theorems, that's your new word for the day, everybody, that you can drop in conversation. Boltzmann's H-theorem, super famous, was the thing that really was sort of making the link between the macroscopic behavior that you see, like, oh, my coffee cup got cold, and this idea that there are atoms, zillions of atoms that are all bouncing into each other, and and that their behavior, collective, that's the important word, their collective behavior, out of it will emerge, out of the individual time reversible behavior of these invisible particles will emerge the collective behavior, like the flow of time. So that was really, that was a really, really profound connection that got made there. Now, I do just want to point out something. When I was learning the H-theorem, my teacher was David Thowles at the University of Washington, Seattle. It was a Nobel Prize winner in condensed matter theory. And he pointed up, he said, by the way, though, there is a problem with this theorem. And in order to make it work, Boltzmann there was a couple things he had to do that really took us away from that sort of pure, remember, we've been arguing against, in the blind spot, we've been arguing against this sort of like idea that science gives us perfect knowledge of the universe, that that's a bit, that God's eye view. And David Thowles said, in order to make this work, Boltzmann had to assume something called molecular chaos. And it basically means that with every collision, after every collision, the system kind of forgets that the collision happened, right? This is just a trick in order to get the calculation to work, because really, every time two things collide, they get correlated, right? I collided with you, you collided with me, now I know about you. But that in order to get the system to work, he had to assume chaos, that basically after the collision, nobody remembers where anybody else is. And that's actually a problem. It's a problem that other people for a long time have tried to work out. I don't think there's ever really been a sufficient response to that. Because what it sort of shows is you kind of have to put something in there by hand to get this to work, right? This collective emergent behavior, we're going to come back to this maybe either in this time or when we really talk about complex systems. That collective emergent behavior is really mysterious, and you can't just get it by taking a bunch of small things, adding them up, tracking them all, and then lo and behold, you get life. That there's really there's some other kinds of physical principle which we don't really fully have a handle on yet, that allows emergence to make something new. So I just wanted to throw that in there, that there's a little bit of a problem with the H-theorem. As a way of describing how, it's just individual time reversible particles that somehow get the one-way flow of time that totally controls the macroscopic world.
Yeah, this is very cool because it's kind of like the amnesia of interactions, right? Basically, you're imposing this sort of amnesia of interactions in the sense of every time you move things forward, they don't remember how they got there. Right. So we're here now. How it happened? We don't know, but let's keep going.
Yeah. Where we're going to lead eventually with thermodynamics and statistical mechanics, because it's going to become the physics part of the foundation for what's called complexity science, which is really, I think, the most important field in physics now. Forget black holes. You can definitely forget string theory. No, black holes are amazing. But, some of the stuff that people think like, oh, this is the most important thing in physics, quantum gravity. I think Marcelo would agree. That's all interesting, yes. But life is actually, complex systems are actually the most important problem in physics. And statistical mechanics and thermodynamics are really physics, the contribution physics makes to complexity science, because it's really multidisciplinary. And this idea of emergence is going to be central, that you can take a bunch of small things, right, that completely their laws, but when you put them together, new, like nature's creative, totally new things can emerge. Things that you could not see in those laws of the atoms, of the small things, you could not predict what is going to emerge out of them at higher levels.
Yeah, and I think it's pertinent to mention that temperature is an emergent phenomenon. What we call temperature, if you go via microscopic behavior, you say, oh, look, there are a bunch of little particles, or molecules interacting, kicking around. There's no temperature there. The temperature is a macroscopic emergent phenomenon that comes from gazillions of molecules interacting with one another, colliding, and at a certain speed. And that's what we're going to relate to temperature. So you cannot talk about, oh, what's the temperature of that molecule? It doesn't work that way. You can talk about a temperature of a collection of molecules because that's the emergent behavior. So it is very important to understand that what statistical physics does, thermodynamics, the fancy, more modern way of thinking about it is, if it's not related to engines, is statistical physics, is that it will bring in probability for the first time into physics. It was not part of the ball game. There was no probability mechanics or electromagnetism, and these guys realized that, look, there's no way we can solve 10 to 24 equations of motion at the same time, but we can treat things on average as groups of things behaving in similar ways, and then you can talk about the probabilities related to these behaviors. And so what Boltzmann would say about the era of time is, he would say, is not that it's impossible for the molecules of perfume to go back into the bottle, but it is incredibly, highly improbable, just because the probability of having all of those collisions work together in the way that would restore all these molecules to that initial ordered state, i.e. inside the perfume bottle, is infinitesimally small. So the era of time for Boltzmann, for this interpretation, is a statistically improbable phenomenon, that you can revert to. So time goes forward because once a system has too many interactions, it's so complex that it cannot revert back to an ordered system, and that is the difference between molecules and the little pencil that goes this way or this way. They can only do that, right?
Yeah.
So it's only one degree of freedom. It goes this way, it goes that way. And when you have systems with many, many particles interacting, you have 10 to the 24, Avogadro number, whatever, it becomes a very different ballgame. And that's where emergent behavior becomes important. Statistical physics, thermodynamics, entropy, life, because life is a mass of particles.
And also, let's talk about, because we only have a few minutes left, let's sort of end on it, because we're going to come back to this, because we could do a whole thing on complexity science. And there's some people we should probably invite, like Chris Kempes or others, to help us sort of sort out complexity, because it's really the frontier of physics right now. And what's cool about complexity theory, it's not just the frontier of physics, it's the frontier of science, because to do complexity science, you need physicists, you need computer scientists, you need biologists, you need ecologists, you need sociologists. It literally touches everything that's complex. But let's just end on the idea of equilibrium versus non-equilibrium, right? Okay. So like we said, equilibrium, my coffee cup has come, it's now the same temperature as the environment. When you're dead, you're in equilibrium, right? And that's really kind of the important thing. Your body just sits there, it's going to decompose. So what is fundamentally interesting about the world is all of life, all complex systems, including even things that aren't life but are complex, like hurricanes, they are far from equilibrium, right? Mm-hmm. So physicists just figured out how to describe equilibrium systems, by the mid 1800s, and then statistical mechanics by the by the early 20th century, they'd nailed that. But far from equilibrium systems like us, because what every cell does is it takes energy and it takes matter and it uses that to drop its entropy. It lowers its entropy. And you're like, how can that be possible? Things can't lower their entropy. Well, they're connected to the environment. What they do is they push their entropy that they're generating by being alive into the environment, right? Mm-hmm. So for a while, they can reduce their entropy, live at a low entropy state, even though they're processing energy, right? But eventually they have to die, right? Eventually that only works for a while, and you're gonna die, and you yourself are gonna, your entropy is gonna rise. So this question of how do far from equilibrium systems, like a cell, like a city, like a termite mound, how do those work? We still are very, very far from understanding that. While the laws of thermodynamics for equilibrium systems are simple to write down, we don't even know what the laws for far from equilibrium system are. And so and yet everything that's really interesting to us, everything we live with, all the, the frontiers of physics now, which is complexity, all those kinds of things, those are all far from equilibrium systems. So super exciting stuff to come.
Yeah, and the atmosphere, right? I mean, you've been writing and thinking about that, so maybe we can use that as an example. Do you want to mention that?
Yeah. So it was James Lovelock, the guy who invented Gaia theory, who first recognized Lovelock had been asked by NASA to in the early 1960s to come and design life experiments. Lovelock was kind of a biochemist, and he realized most of the things people were talking about was looking for microbes on Mars. I think we talked about this last week a little bit. And he was like, how do you know there's going to be microbes on Mars? How do you know what Martian life is going to be like? But he very quickly realized that the atmosphere of Mars told you something immediately about life, which is that there can't be a lot of life because the atmosphere is in equilibrium. The atmosphere, the chemical reactions of the stuff in the Martian atmosphere are mostly, there's a little bit of other stuff going on, but mostly it's reached equilibrium. Whereas the atmosphere on Earth with its oxygen is far from equilibrium. If life wasn't pumping oxygen into the atmosphere to keep it at 21%, oxygen, if you turned life off, then very quickly all that oxygen would react with rocks, would get pulled out of the atmosphere, and the Earth's atmosphere would return to chemical equilibrium, which is just like the thermal equilibrium in the cup. And so because Earth's atmosphere is so far from chemical equilibrium, you can tell there's life in it. And that's actually the source of how we're going to find life on other planets. One way is we're going to look for atmospheres that are out of equilibrium because it's life that's pushing it there. So that's great, Marcel. It's a nice application of this thermodynamic statistical mechanics idea of equilibrium and non-equilibrium as it relates to something as profound as looking for life on other planets.
It's a beautiful connection between thermodynamics and astronomy, which,
right.
Wow, right? It's something that, people do think about, the sun is at a certain temperature, stars have a certain surface temperature and core temperature and etc. But life is the real alchemist in a sense when it comes to the atmosphere.
Nicely put. I like that. Life is the real alchemist. That's really true. Yeah. It makes impossible things happen. Life makes impossible things happen thermodynamically. And in many ways, we do not understand how it does that. And it is a question as profound as the space-time around a black hole, right? Or, the birth of the universe, right? Because that's how consciousness emerges. Somehow out of that emerges sentience and consciousness, which really, as we like to say, there's no third-person view. So this first-person view we are stuck with emerged out of this mystery of how life does its thermodynamics.
I just had this crazy thought, which is, given that intelligence is an outcome of all forms of life, intelligence, which is the thing that we use to tell the story of who we are, is the ultimate non-equilibrium manifestation. In equilibrium, there is no intelligence. There cannot be intelligence in equilibrium, right? Because you need to be shuffling information from one point to another, and that costs energy, and you have to keep feeding the machine and still keep the low entropy. And so life is an engine that only works because it's not out of equilibrium. Intelligence, being part of life, is so we are the non-equilibrium thermodynamics of the universe telling its own story.
All right, and we're going to leave it at that, because really, where else could we go from anywhere else after that? From that peak is just downhill to McDonald's or whatever. So we're there. So we'll end there. And we promise we will come back to you with more on thermodynamics, the 20th century, 21st century, and complexity theory. Hopefully have some guests along those lines. And so there you go. So thank you very much, everybody, and we'll see you next time.
See ya.